Recent research in cosmology has raised a remarkable possibility. Earth, the Milky Way, and our entire galactic neighborhood may be located inside a massive, low-density region of the universe, a cosmic void. Unlike the smooth, evenly filled universe we once imagined, this scenario suggests our surroundings could contain far less matter than average, stretching across billions of light years. So, watch this video till the end and subscribe to the channel. Let's begin. Scientists exploring the large-scale structure of the cosmos have proposed that our home, from the solar system to the Milky Way and even the local group of galaxies, might reside inside a vast region of unusually low matter density. Instead of being situated in an average part of the universe, we could be drifting within a colossal, underdense bubble, sometimes described as a cosmic void, stretching perhaps 2 billion light-years across. To put that into perspective, this would be far larger than any previously identified nearby void and dramatically bigger than what standard cosmological models would normally predict for our region of space. Such a structure wouldn't be entirely empty, but it would contain significantly fewer galaxies, less gas, and less overall mass than the surrounding cosmos, leaving us cocooned inside a space that subtly affects how light, matter, and even the fabric of cosmic expansion behave around us. The most surprising part of this proposal is how dramatically it challenges long-held assumptions. For decades, astrophysicists believed the universe becomes smooth and uniform when viewed on large enough scales. However, if we truly occupy a void of this magnitude, that assumption loses stability. A 2 billion light-year void isn't a small anomaly. It's a structure so huge that it could influence cosmological measurements across the board. The concept suggests that everything from galaxy movement to the acceleration of space itself might look different when observed from inside such an environment, meaning our measurements could be subtly biased simply because of where we happen to exist. This hypothesis didn't emerge from speculation alone. It arose from growing tension between observations and expectation. As scientists mapped galaxies across deeper and wider areas of the universe, hints of underdensity around our cosmic neighborhood began to appear. Instead of galaxies becoming more plentiful with distance, surveys found that the number of nearby galaxies seemed lower than expected, almost as if we were sitting near the center of a vast hollow. If this underdense region truly spans billions of light years, then it would represent one of the largest known structures of its kind, dwarfing famous voids like the BAOs void and pushing the boundaries of what cosmological theory says should exist. The idea isn't universally accepted, far from it, but it's compelling enough that many researchers have begun re-evaluating how a structure of this scale might form and what clues it leaves behind. It also opens the door to deeper questions. Is our position in the universe more special than we assumed? Could being inside a void affect the rate at which we think the universe expands? And if such a void exists, what does it suggest about the early universe and the evolution of cosmic matter? The idea that we may live inside a massive cosmic void gained traction not from casual observation, but from a remarkable method of studying the early universe, by listening to the echo of its birth. After the Big Bang, the infant cosmos behaved almost like a ringing bell. Waves of pressure rippled through the hot plasma of particles and light, expanding outward and leaving behind faint imprints in the distribution of galaxies we see today. These relic ripples are known as baryon acoustic oscillations, often described as the sound waves of the Big Bang frozen into space itself. Billions of years later, they give astronomers a way to measure cosmic structure with astonishing precision, acting like fingerprints of the universe's earliest moments. By mapping how far apart galaxies are, researchers track the size of these primordial ripples. In a perfectly uniform universe, the spacing should look consistent no matter where we observe. But something unexpected appeared. A subtle drift in this pattern that hinted our local region may not match the density of more distant space. When astronomers compared ripples nearby to those seen across much greater distances, they found that the large-scale structure around us seemed slightly stretched, as if space locally expanded faster than average. That kind of stretching is exactly what one would expect if we lived inside an immense, underdense void, where fewer gravitational anchors exist to slow the expansion of space. The logic is simple but powerful. A void contains less matter, less gravity, and therefore less resistance to expansion. So, if baryon acoustic oscillations look slightly larger or more widely spaced in our vicinity, it suggests our cosmic neighborhood may be expanding faster than regions with higher density. This deviation doesn't conclusively prove the existence of a void, but it strengthens the case, especially when paired with galaxy surveys that already show hints of lower density near us. Taken together, the ripples of the Big Bang and the layout of galaxies begin to form a story. One in which the Milky Way isn't just drifting through an ordinary patch of space, but through a vast and quiet expanse sculpted by ancient cosmic vibrations. Baryon acoustic oscillations play a central role in modern cosmology because they give researchers something incredibly valuable: a built-in measuring stick for the universe. These ancient pressure waves, frozen into the distribution of galaxies, have a known physical scale that formed about 380,000 years after the Big Bang. Since their size is well understood, scientists can use them the way a surveyor uses a ruler. By comparing the spacing of galaxies at different distances, they can calculate how space has stretched over time. Every place these ripples appear, near or far, acts as a marker that tells us how large the universe has become at that moment in cosmic history. Because the BAO scale is consistent, any deviation from the expected spacing raises a flag. If the ripples appear slightly larger or smaller in one region than in another, it suggests that space there has expanded differently. That sensitivity is what makes BAOs such a critical tool in detecting unusual cosmic environments. In a dense region full of galaxies, gravity slows expansion, compressing the perceived BAO scale. In a void, where matter is scarce and space expands more freely, the scale appears stretched. This contrast allows scientists to detect subtle unevenness in the universe that would otherwise be invisible on such massive scales. When researchers noticed that the BAO spacing near our cosmic neighborhood might be slightly different than the spacing measured farther away, it became an important clue. Not definitive proof, but a compelling hint that we might live somewhere special. Without these ripples acting as a cosmological yardstick, the potential void surrounding us could have gone unnoticed for much longer. BAOs give cosmology a consistent reference point across billions of light years, making them indispensable for testing cosmic uniformity and uncovering anomalies that challenge our assumptions about structure, density, and expansion on the grandest scales. The mystery deepens when we confront one of the most pressing puzzles in modern astrophysics: the Hubble tension. This ongoing conflict revolves around a deceptively simple question: how fast is the universe expanding? For decades, astronomers assumed this could be answered with a single number known as the Hubble constant, a value that describes how quickly galaxies move away from each other as space stretches. Yet the deeper scientists look, the more troubling the results become. Local measurements based on nearby galaxies and supernovae consistently yield a higher expansion rate. Meanwhile, methods that observe the deep universe, especially those using the cosmic microwave background, produce a slower expansion rate. These two values should match if our cosmological model is correct. Instead, they disagree by a margin too large to dismiss as error or coincidence. Local measurements rely heavily on what's close to us: Cepheid variable stars, type Ia supernovae, and distance ladders that build upon well-calibrated steps. These methods indicate that space is expanding at roughly 73 kilometers per second per megaparsec. But when astronomers calculate the expansion using ancient light from the early universe, such as the cosmic microwave background, measured by missions like Planck, they find a lower value of about 67 kilometers per second per megaparsec. This discrepancy isn't minor. It's significant enough to force cosmologists to question whether something fundamental is missing from our understanding of the cosmos. Every new round of measurements, refined with greater precision, keeps reinforcing the divide rather than closing it. Instead of fading, the tension grows sharper. If both measurements are correct within their respective domains, and current evidence suggests they might be, then something in the universe must be influencing the local expansion differently from the global average. This is where the possibility of a cosmic void enters as an intriguing solution. A low-density region would have weaker gravitational pull compared to denser parts of the universe, making it expand faster internally. That means if we're living inside such a void, our local measurements could naturally appear higher because we're observing expansion from the inside of a rapidly stretching bubble. Meanwhile, cosmic microwave background observations reflect the universe as a whole, averaging over denser regions and slower expansion rates. The discrepancy, then, wouldn't be an error. It might be a direct consequence of our unusual cosmic environment. The Hubble tension challenges the very core of the standard model of cosmology, known as lambda CDM. This model assumes the universe is homogeneous and isotropic on large scales. In other words, smooth and uniform everywhere. But if our region is significantly underdense compared to the cosmic average, this assumption weakens. It means that where we are matters, not just how we measure. It means that cosmic expansion might not be the same everywhere, despite the elegance and simplicity of our equations. And it means that the disagreement between local and global expansion rates could be a feature of reality rather than a flaw in data. Astrophysicists around the world continue to debate the best interpretation of the Hubble tension. Some argue for new physics. Perhaps dark energy behaves differently than we thought, or the early universe evolved in unexpected ways. Others think the answer may lie in local cosmic structure rather than exotic forces. If a void surrounds us, stretching 2 billion light-years across, as some studies propose, then its effect could be large enough to influence the expansion measurements we take nearby. This wouldn't require rewriting the laws of physics, just acknowledging that our cosmic neighborhood is more unusual than assumed. No single explanation has risen as the definitive answer. Yet the Hubble tension remains impossible to ignore. It is one of the clearest signs that something about the universe is not fully understood, and every new observation acts like a spotlight illuminating the cracks in our models. The idea of a void is compelling not because it is proven, but because it fits the puzzle so cleanly. It offers a bridge between two conflicting truths, a way to reconcile growth and history, expansion and origin. And as research continues, the tension between local and distant measurements remains one of the strongest motivations to explore the possibility that we are living in a cosmic hollow. If the universe around us is not uniform, If instead we find ourselves inside a vast, underdense bubble stretching billions of light years, then the expansion of space within that bubble may not behave the same way it does elsewhere. Gravity is the key to understanding why. In regions where matter is dense, galaxies and dark matter exert more gravitational pull, slowing the expansion of space like weights on a rubber sheet. But a void, by definition, has far less mass. With fewer galaxies and less invisible dark matter to hold space together, expansion can proceed more rapidly. It's like comparing a taut net to one with missing knots. The looser sections stretch more easily. If Earth and the Milky Way lie within such a loosened region, then the Hubble constant we measure locally, using nearby stars and galaxies, would naturally appear higher than measurements taken from observations that encompass the entire universe. This provides a strikingly natural way to resolve the Hubble tension. Instead of requiring exotic new physics or unknown forces, it simply states that our perspective is biased by where we are. When astronomers measure supernova distances or track the redshifts of nearby galaxies, they're effectively sampling expansion from inside our bubble, where the stretching is faster because gravitational resistance is weaker. Meanwhile, data from the cosmic microwave background, radiation that fills the universe and reflects conditions billions of light years away, captures the expansion rate outside of our local environment. If the cosmos beyond our void expands more slowly, then the lower CMB-derived Hubble constant suddenly makes sense. We're comparing two environments with two different gravitational landscapes, and naturally, they don't match. This idea gains credibility from simulations showing that voids do accelerate local expansion. When cosmologists model how matter distributes over time, voids tend to open up like hollow scars in the cosmic web. The regions inside them stretch and thin as galaxies drift outward, pulled toward denser walls and clusters. Over billions of years, the void becomes emptier, and the expansion within it continues to outpace the average. If we inhabit such a region, then our local cosmic measurements would be like observing a river from inside its strongest current, instead of from the calm water along the banks. The flow appears faster, not because the entire river is speeding up, but because we're standing in the part where the motion is most intense. The scale of the proposed void is critical. Small voids are common in the universe, but they are too insignificant to meaningfully shape expansion on a cosmological level. However, an underdense region, 2 billion light-years wide, vast enough to rival the largest known structures, could absolutely tilt our observations. Such a void would sit at the threshold where local physics begins to masquerade as global truth. And if our galaxy lies near the center of this bubble, the effect becomes even more pronounced, because expansion inside the void would appear almost isotropic, evenly expanding in all directions, even though it differs from the universe beyond it. Critics of the void hypothesis argue that a structure this large would be incredibly rare, perhaps too rare to be likely. Yet rarity isn't impossibility. The cosmos is a vast and unpredictable place, and improbable configurations still occur within its grand architecture. If we are a statistical outlier, residents of a strangely vacant patch of the universe, then many assumptions built into our cosmological measurements must be re-examined. Everything from dark energy estimates to calculations of universe age may shift once we correct for the gravitational lens of emptiness surrounding us. The most exciting aspect of this idea is that it doesn't seek to replace known physics. It simply reinterprets data through a different spatial context. A void could account for why nearby supernovae suggest one expansion rate, while ancient light implies another. It brings coherence to a tension that has resisted resolution for years. Instead of forcing us to invent new forms of matter or rewrite cosmological laws, it invites us to look around and reconsider the possibility that the universe isn't as uniform as we believed. If our cosmic home is a hollow, then we are observers watching the universe from inside a bubble, experiencing space-time differently than observers far beyond its edges. Whether this void exists remains unconfirmed, but it offers a breathtaking explanation for one of cosmology's greatest modern puzzles. If proven, it will not only diffuse the Hubble tension, it will redefine our cosmic context and remind us that our view of reality is shaped not just by what we see, but by where we stand within the universe. Inside a cosmic void, matter behaves very differently than it does in dense galactic clusters. Gravity is always the sculptor, always the guiding force, and gravity naturally draws matter toward concentration. In a region filled sparsely with galaxies, there simply isn't enough mass to pull everything inward. Instead, matter gradually migrates toward the edges of the void, flowing outward over cosmic timescales like water draining away from the center of a shallow basin. The result is a self-intensifying process. As matter escapes, the void becomes even emptier, and as it grows emptier, it loses even more gravitational influence, accelerating the outward drift. In this way, voids do not vanish with time. They expand, quietly and steadily, becoming darker, quieter, and more vacant as the universe ages. The edges of large voids often feature walls of galaxies, filaments, and clusters, immense cosmic highways where matter accumulates after billions of years of gravitational migration. These filaments form the backbone of the cosmic web, and voids become the open spaces in between, like vast interstellar deserts carved by gravity's slow hand. If we are inside one of these empty expanses, then our galaxy may be slowly drifting outward toward one of these denser walls, even if the motion is subtle on human timescales. Over billions of years, galaxies inside a void experience what might be called a gentle gravitational push, drawn toward the more massive structures beyond their hollow environment. This flow of matter outward has several consequences that astronomers can look for. Galaxies in voids often have slightly higher velocities relative to the cosmic average because they are being pulled toward dense regions beyond the void's boundary. These motions can distort redshift measurements, making objects appear to move faster or slower depending on direction. Such distortions, when mapped across thousands of galaxies, can reveal whether we are embedded within an underdense structure, a signature like ripples in water that show the shape of the pond beneath. If our local group is slowly drifting outward, then that motion could contribute to the apparent increase in local expansion rates, reinforcing the possibility that we are witnessing the universe from inside a gravitationally relaxed zone with minimal resistance. Another consequence of matter flowing outward is a lower galaxy formation rate inside the void. With fewer raw materials, less hydrogen, less dark matter scaffolding, galaxies form more slowly and remain smaller on average. They may have fewer massive starburst episodes and fewer rich clusters. This means that if we are living inside a void, our region should host fewer bright and densely packed galaxies compared to more distant cosmic neighborhoods. Observational surveys indeed suggest a deficit of nearby galaxies, a finding that aligns with the flow outward behavior expected from void evolution. The lack of density is not simply a snapshot, it's a long-term outcome created by billions of years of matter migration. The gravitational dynamics of voids also influence the shape and motion of galaxy clusters on their periphery. Clusters bordering a void can appear to stretch or shear, drawn toward one another along filaments, while leaving a widened emptiness behind. The motion isn't chaotic. It follows gravitational gradients like iron filings following magnetic field lines. If Earth lies somewhat centrally within such a region, then our view of distant galaxies might be subtly anisotropic, not perfectly identical in every direction. This is one reason why the void hypothesis is so compelling. It offers explanations not only for expansion rate discrepancies, but also for unusual motions seen in certain galaxy catalogues. All of this paints a picture of a universe that is not evenly filled, but dynamically sculpted. Matter pooling where gravity is strongest and drifting away from places where it is weak. Voids, instead of being rare anomalies, are natural consequences of cosmic evolution, and extremely large ones, while uncommon, are not unthinkable. If we inhabit one, then our cosmic environment is not simply empty, it is actively emptying, gradually clearing itself out as galaxies slip outward toward denser cosmic highways. Living inside a void wouldn't change our day-to-day lives, but it could profoundly reshape our interpretation of the cosmos. The behavior of matter in such a region is slow, subtle, and immense, a movement only visible through deep sky mapping and careful measurement. Yet over cosmic time, its effect is transformative. Voids hollow themselves out more and more, making the universe appear to expand unevenly depending on where one stands. For us, this could mean that some of the deepest cosmological mysteries aren't hidden in the far reaches of space, but woven quietly through the vast emptiness surrounding us. This pattern of matter flowing outward into denser regions leads naturally to another key line of evidence, what we observe when we count galaxies across the sky. If we truly live inside a massive cosmic void, then the distribution of galaxies around us should reflect that emptiness. Surveys that map the large-scale structure of the universe do exactly this. They scan enormous stretches of sky, cataloguing hundreds of thousands, sometimes millions, of galaxies to build a three-dimensional picture of cosmic architecture. And as these maps have grown more precise, a subtle but persistent trend has emerged. Our local region appears to host fewer galaxies than expected. Multiple large surveys, including the Sloan Digital Sky Survey, SDSS, and others that probe deeper into cosmic distance, consistently report a dip in galaxy density near our position in space. Instead of the numbers rising predictably as we look further out, as would be expected in a perfectly uniform universe, the galaxy count remains lower than models forecast for our immediate cosmic surroundings. Only when we push measurements farther, beyond hundreds of millions of light years, do we begin to see density approach what cosmologists consider typical. The structure builds outward, like leaving the center of a sparse valley and approaching the foothills at its edge. This kind of underdensity is exactly what theorists would predict if we are living within a megavoid. The scale of the deficit is what makes the finding remarkable. Small voids are common, and they pepper the universe like air pockets in bread. But the underdensity suggested by these surveys stretches far beyond local clusters, extending outward into regions so large that they hint at a structure possibly approaching 2 billion light-years across. If this is correct, then we are not just near a void. We are submerged in one. The Milky Way would be floating in the hollowed-out heart of a massive cosmic depression, surrounded at extreme distances by denser walls where galaxies pool like rainwater, collecting along a landscape's rim. Research teams analyzing these patterns have found that the galaxy count isn't just lower. It declines smoothly toward our position, implying that the center of the underdensity may be very close to us. This aligns strikingly with the idea that our vantage point is near the void's interior rather than its boundary. If we were located near the fringe, the pattern would look uneven, with one side more populated than the other. Instead, the decrease appears broadly symmetrical, suggesting our cosmic address may lie uncomfortably close to dead center in a region of noticeable emptiness. Some astronomers remain cautious, emphasizing that cosmic structure can be complex and patchy even when averaged on large scales. Yet the consistency across independent surveys strengthens the void hypothesis. Different teams, different instruments, and different statistical methods converge on a similar conclusion. Galaxy density around us is lower than expected, not drastically empty, but low in a way that becomes unmistakable when observed across hundreds of millions of light years. If future surveys continue to confirm these patterns, the implications grow profound. It would mean our local cosmic environment is not representative of the universe as a whole. It would mean that the measurements we take from nearby galaxies, including those used to estimate expansion, may be influenced by the very emptiness around us. And it would mean that the Hubble tension, one of cosmology's greatest puzzles, may not require mysterious new physics at all, only an acknowledgement that we inhabit a less crowded neighborhood than we assumed. The idea that we may live inside a massive cosmic void directly confronts one of the foundational assumptions of modern cosmology, that the universe is homogeneous and isotropic on the largest scales. For decades, the standard model of cosmology, known as lambda CDM, has operated on the belief that no location in the universe is special or privileged. This principle, called the cosmological principle, asserts that if you zoom out far enough, matter should be evenly distributed in every direction. No cosmic neighborhood should differ drastically from another. But if our region is significantly underdense, if we sit inside a hollow billions of light years across, then our place in the universe may be more unusual than previously assumed. Suddenly, the assumption of large-scale uniformity becomes uncertain, and the standard model begins to flex under the weight of a new possibility. A void of the proposed magnitude challenges cosmology, not because voids are unnatural, but because one this large would be extreme. Voids hundreds of millions of light years across are well known. They lace the cosmic web like immense pockets between dense galaxy clusters. But a void spanning 1 to 2 billion light years would not be just another gap in the structure. It would be one of the largest ever discovered. The existence of such a structure would force cosmologists to confront the possibility that large-scale uniformity might take much longer to emerge than assumed. Instead of the universe smoothing out like a perfectly risen loaf of cosmic bread, it might remain uneven, even at enormous scales, textured by pockets of emptiness and dense filaments carved by gravity over billions of years. If we truly inhabit the interior of such a void, then many of our measurements become viewpoint dependent rather than universal. Values like the Hubble constant, long treated as fixed quantities, might vary depending on where an observer exists. Observers inside a void would measure faster expansion because their environment is less gravitationally constrained. Observers outside the void, in denser cosmic terrain, would see slower expansion. This variability forces a re-evaluation of how cosmological data is interpreted, especially when comparing measurements drawn from local galaxies versus the ancient light of the cosmic microwave background. Instead of proposing new physics to explain the divergence, the void hypothesis suggests that both sets of measurements may be right, each from their own vantage point. The core challenge this poses is conceptual rather than mathematical. It requires accepting that our position in the universe is not average. For centuries, science has moved steadily away from the notion of Earth being central or special. First, we learned we were not the center of the solar system. Then we learned the Milky Way was not the center of the universe. Now, the void hypothesis forces us to reconsider whether our region of space might be something of an oddity, less filled, less massive, and more rapidly expanding than the cosmic norm. Not central, but still unusual. This doesn't violate the laws of physics, but it does require cosmology to loosen one of its most cherished simplifications. A universe with large-scale inhomogeneities complicates cosmological interpretation. Many conclusions drawn about dark energy, galaxy evolution, and even the age of the universe rely on the assumption that space behaves uniformly when viewed broadly. A giant void breaks that symmetry. If the local universe expands faster than the average, then supernova data, which helped reveal dark energy, may need reinterpretation. If density varies drastically across billions of light years, then the cosmic microwave background and galaxy surveys may not be measuring the same universe from the same structural context. This complicates model building, but it also makes cosmology richer, more dynamic, more nuanced, more alive. This is why the possibility of a void is not just interesting, it is disruptive. It forces researchers to ask whether simplicity was mistaken for truth. It urges caution, curiosity, and creativity. And it drives new efforts to map the cosmos in greater detail than ever before. Because if our region is underdense at a scale this enormous, then the universe may be far more textured and surprising than our current models assume. The idea that we may live in a giant cosmic void isn't something that appeared overnight, nor is it a concept born out of desperation. Void-based explanations have circulated in cosmology for decades, resurfacing whenever observational data revealed inconsistencies that standard models struggled to explain. As far back as the early 2000s, some researchers proposed that the universe's acceleration, attributed to dark energy, might instead be a byproduct of us occupying a large underdense region. Their argument suggested that if we reside in a vast low-matter bubble, then distant galaxies would appear to accelerate away, not because of dark energy, but because space outside the void expands more slowly than inside. The contrast would be subtle yet profound. The universe would look like it's accelerating even if no mysterious repulsive force exists at all. Most cosmologists were skeptical. The void required to mimic cosmic acceleration without dark energy would need to be enormous, far larger than any void confidently observed at the time. The idea was compelling, elegant even, but it challenged the prevailing model too directly. Researchers weren't prepared to dismiss dark energy, a solution that neatly fit most observational data. For many years, the void hypothesis was pushed to the fringes of theoretical cosmology, treated as an intriguing yet unlikely alternative. It was not rejected outright, but placed on the shelf, a possibility waiting quietly for more evidence. Yet, the idea never fully disappeared. Instead, it matured. As surveys expanded, mapping more of the cosmos with greater precision, signs of large-scale underdensity began to accumulate. Studies revealed unexpected dips in local galaxy counts, peculiar velocity flows, and measurements of the Hubble constant that refused to converge. These anomalies breathed new life into the void hypothesis. Researchers who once set it aside began revisiting it, refining models, and testing whether a massive void could resolve multiple tensions at once: expansion rates, density variations, and even hints from baryon acoustic oscillations. Gradually, what once was fringe became something worthy of renewed scrutiny. It's important to recognize that skepticism remains strong, and not without reason. A void large enough to explain these cosmological tensions would be rare, statistically improbable, and challenging to reconcile with early universe inflation models. Many physicists argue that inflation should have smoothed out the cosmos more uniformly, making such a megavoid an unlikely leftover. Others point out that while underdensities exist everywhere, observing one with such dramatic scale may require a fortunate or extraordinary position in the universe. Being inside such a void doesn't break physics, but it does make us cosmological outliers. Still, the persistence of the void hypothesis speaks volumes. Ideas that survive decades of scrutiny do so because data refuses to let them die. Every time new measurements emerge, from supernovae brightness, from galaxy surveys, from the structure of BAOs, the void alternative resurfaces to offer coherent explanations. It remains neither proven nor dismissed, sitting on the boundary between possibility and discovery, waiting for observational clarity to tip the scales. Some scientists embrace it cautiously, others defend it passionately, and many more watch with growing curiosity. Few theories remain active this long unless nature continues whispering in their direction. Void-based models highlight something powerful about science. Progress doesn't always move in a straight line. Sometimes answers emerge not by replacing old ideas, but by recovering ones that were set aside when evidence was thin. The void hypothesis may or may not be the truth, but its resilience shows that the universe often leaves doors open, even when we think we've closed them. Despite its elegance and its ability to tie multiple cosmological puzzles together, the void hypothesis remains an open question. Intriguing, suggestive, yet far from confirmed. In fact, many astronomers emphasize caution when approaching this idea. Just because the hypothesis fits certain observations does not mean it is the only explanation, nor even the most likely one. The universe has a habit of presenting patterns that appear meaningful, but require deeper verification before conclusions can be drawn. Scientists must distinguish between models that are convenient and models that are real. And that process takes time, evidence, and scrutiny from multiple angles. Researchers remain aware that many factors could be influencing the expansion measurements without requiring us to live inside a megavoid. Systematic errors in distance calibration, limitations in cosmic microwave background modeling, or unknown behaviors of dark energy could also contribute to the discrepancy known as the Hubble tension. Even the methods for measuring the expansion rate locally depend on assumptions about supernova brightness, about Cepheid variables, about redshift values that may contain subtle biases. If even one piece of that observational ladder is slightly off, the resulting expansion rate might appear faster than it truly is. Scientists are actively refining each rung of that ladder, checking and rechecking the numbers, ensuring that no single measurement is misleading the entire field. Additionally, the cosmic microwave background, a snapshot of the universe when it was just a baby, still aligns remarkably well with the standard cosmological model. If a void of extraordinary size surrounds us, some cosmologists argue that the imprint of such a structure should be more obvious in temperature fluctuations across the CMB sky. So far, the evidence is mixed. Some researchers claim to see subtle temperature alignments that could match a void scenario, while others argue these signals can be explained without invoking a massive underdensity. Until the data becomes unambiguously clear, the scientific community remains divided, curious, alert, but cautious. This caution is not resistance to new ideas. It is the foundation of science itself. Cosmology thrives on evidence, not enthusiasm. For a hypothesis to reshape our view of the universe, it must withstand repeated testing, replication, and critical review. The void idea is compelling precisely because it invites these tests. It makes predictions that future surveys can confirm or refute. It offers a framework to evaluate new data, rather than patching theories with ad hoc explanations. But until these predictions are verified, until we can say with confidence that our cosmic neighborhood is significantly emptier than distant regions, the hypothesis remains just that, a possibility, not a conclusion. Some researchers warn that we should avoid falling into anthropocentric assumptions. After centuries spent proving Earth is not cosmically central, it may feel counterintuitive to suggest we occupy a special or rare environment. The universe has no bias toward our presence. If we are in a void, it is coincidence, not cosmic intention. Others caution that relying too heavily on the void explanation may slow exploration into alternative solutions to the Hubble tension. If dark energy behaves differently than assumed, or if new physics underlies cosmic acceleration, then focusing solely on structure could blind us to deeper truths. The best scientific progress comes when multiple possibilities remain active until evidence rules out all but one. And yet, the persistence of the void hypothesis reveals something important. The universe is not yielding its secrets easily. Even now, with more instruments, more surveys, and more data than any generation before, the expansion rate of space remains a paradox. It refuses to flatten neatly into a single number. Local and global measurements diverge like two voices singing similar but not identical melodies. The void theory offers one way to unify those voices, but until observational confirmation arrives, it must stay on the edge of accepted cosmology, a bold possibility waiting for verification. Scientific caution is not skepticism meant to suppress new ideas. It is the guardrail that keeps discovery honest. It ensures that every claim meets the highest standard of evidence before rewriting the story of the cosmos. The void may be real. It may explain the Hubble tension and reshape our understanding of where we live in the universe. Or the answer may lie somewhere entirely different, hidden in dark energy, early universe inflation, or physics not yet imagined. For now, researchers explore all paths, the void included, knowing that truth in cosmology is earned slowly, through patience, persistence, and evidence that speaks louder than theory. If the void hypothesis were to be confirmed, if future surveys revealed beyond doubt that the Milky Way resides in the vast interior of a multi-billion light-year underdense region, the implications for cosmology would be transformative. It would not simply add a footnote to our understanding of the universe. It would rewrite the structure, assumptions, and interpretive lens through which nearly all cosmic measurements are viewed. Modern cosmology is built upon the idea that the universe is smooth at the largest scales, that matter distribution averages out, and that observers anywhere would measure roughly the same expansion rate. A confirmed local void would shatter that foundation, forcing scientists to account for the influence of spatial position on nearly every observational conclusion we draw about the cosmos. One of the most significant consequences would involve dark energy, the mysterious force believed to be accelerating cosmic expansion. If we live inside a void that expands faster than the surrounding universe, then part of what we interpret as acceleration may actually be a local effect, rather than a universal constant. This doesn't necessarily eliminate dark energy, but it may reduce the amount required to fit observational data. The universe may still be expanding faster overall, but the rate we measure from our interior viewpoint could be artificially inflated by our environment. In such a scenario, the balance of cosmic ingredients, dark matter, dark energy, and normal matter, would need recalibration. The dark energy density might be lower than estimated, or its behavior may be more complex than a simple constant acting uniformly through space. Matter distribution would also require major re-evaluation. Instead of a universe where matter is evenly sprinkled across the cosmic web at very large scales, we would confront a universe whose structure retains variation even in its vastest stretches. The existence of a void of such scale implies that gravitational evolution may produce greater extremes than previously believed, deeper deserts and richer clusters. That means simulations of cosmic formation must account for scenarios where voids stretch beyond expected statistical limits, suggesting that initial fluctuations in the early universe could have been more dramatic or persistent. It could also influence how we interpret galactic motion, redshift surveys, and gravitational lensing, all of which rely on assumptions about uniform matter distribution. The story of cosmic evolution would change as well. A void does not remain static. It deepens over time as matter flows outward. If we are watching the universe from inside such a region, then we are witnessing an advanced stage of a natural process. The long-term separation of dense and empty regions under the influence of gravity. Our observations of galaxy formation, star abundance, and even hydrogen gas distribution would need to be filtered through the lens of this environment. Galaxies inside voids evolve differently, often more slowly, forming stars less efficiently due to reduced material availability. If our environment is underdense on a massive scale, then the Milky Way itself may be a product of unusual cosmic conditions, shaped not only by its own history, but by the quiet, sparse space it inhabits. Another implication is philosophical and profound. Humanity has repeatedly discovered that we are not central in the cosmic narrative, not the center of the solar system, not the center of the galaxy, not the center of anything. Yet, if we live within one of the largest underdense regions in existence, we occupy a rare kind of cosmic address, not central in power or importance, but statistically unusual. Our environment could be a cosmological exception rather than the norm. That forces scientists to reconsider how universal our observations truly are. Are the laws we measure from Earth universally applicable, or are some influenced by local conditions? Could intelligent observers elsewhere in denser regions measure different expansion rates, different galaxy behavior, even different cosmological parameters? If proven true, the void hypothesis would push cosmology toward a more location-dependent understanding of the universe, a model where context matters, where the value of the Hubble constant may differ depending on where it is measured, and where cosmic acceleration might appear stronger or weaker based on environmental density. It would encourage a shift toward cosmological cartography on unprecedented scales, mapping not only where matter exists but how its distribution warps perception, light, and expansion itself. Such a discovery would mark a new era, not a breakdown of science, but an evolution of it. The universe would become not less understandable, but more intricate, a place where structure influences perception, where position shapes truth, and where cosmic emptiness holds as much importance as cosmic abundance. If we are indeed living inside a void, then the universe is telling us something extraordinary. That emptiness itself is a force, a scaffold shaping the very measurements we use to understand reality. Living inside a cosmic void would fundamentally change how we describe our position in the universe, not geographically, but philosophically and scientifically. For generations, astronomy has worked to dismantle the idea that Earth holds a privileged position in the cosmos. The Copernican revolution taught us we are not the center of the solar system. The discovery of the Milky Way structure showed we are not near the center of our galaxy. and later observations confirmed we are not at the center of the universe. There is no center at all, not in the traditional sense. Yet, if we truly reside in a vast underdense cosmic void, then our location may be unique in a way cosmologists never expected. Not central, not special, but statistically unusual. We would inhabit an environment that is different from most regions in the observable universe, defined not by abundance, but by absence. Our cosmic address has always been described in layers: Earth, Solar System, Milky Way, Local Group, Virgo Supercluster, Laniakea. But if the void hypothesis is correct, there is another label to add beyond those familiar structures: a member of a giant underdense region spanning perhaps 2 billion light-years. That would mean the space surrounding us is not average cosmic real estate. It would be a sparsely populated celestial countryside, far from the bustling galactic cities and dense clusters that fill other regions of the universe. The Milky Way would be like a lone farmhouse surrounded by vast stretches of empty cosmic field, with the nearest neighboring galaxies spread thin like distant lanterns on a dark horizon. This reframes how we think about ourselves in relation to the universe. Instead of floating in a uniform sea of galaxies, we may be drifting in a cosmic gulf, a place where matter is scarce and gravity is weak relative to the outside. Such an environment could subtly color our view of the cosmos. It could make galaxies appear to be rushing away faster than they truly are. It could make expansion seem more dramatic from our perspective than from one located in a denser region. In other words, our cosmological measurements might carry the imprint of our location, the way a traveler in a valley sees the landscape differently than someone standing atop a mountain. If Earth exists inside a void, our vantage point becomes not just a window into the cosmos, but a lens shaped by emptiness. Light traveling to us would cross regions of lower density, where gravitational fields are weaker and the expansion of space is more pronounced. This could influence brightness, redshift, and distance measurements, meaning that what we observe about distant galaxies and supernovae may reflect not only universal physics, but our placement within a naturally fast-expanding cavity. We would need to translate our observations through that context, the way astronomers account for atmospheric distortion when observing stars from Earth's surface. There is also a more personal dimension to this realization, a shift in cosmic perspective. For centuries, we have understood ourselves by dethronement. Every scientific revolution has pushed humanity farther from cosmic centrality. But the possibility of living in a giant void offers a strange new form of significance, not born of importance, but of rarity. We may be witnesses to the universe from a vantage point few other observers could experience. A civilization in a dense cluster might see a cosmos teeming with galaxies, brighter skies, stronger gravitational interactions, more cosmic fireworks. We, instead, may gaze outward from a region where galaxies are fewer and farther apart, where the darkness between them is wider, where cosmic evolution unfolds more slowly. This raises fascinating questions. If intelligent life exists elsewhere in the universe, and statistically, it likely does, their scientific conclusions could differ depending on where they are located. A species evolving in a dense cluster might measure a slower local expansion rate, perhaps inferring a different value for cosmological constants than we do. If we met such a civilization and compared observations, would we realize that the universe looks different depending on where one stands? Would we discover that cosmic truth is partially shaped by cosmic address? Even our understanding of visibility could shift. The night sky is already mostly empty to the naked eye. Thousands of stars out of billions in our galaxy and only a handful of visible galaxies beyond. But if we are inside a void, then what is absent from the sky matters just as much as what is present. A denser region might reveal far more galaxies with the same telescope power. We are observing from a cosmic, low-density window, where the universe's structure appears stretched, quiet, and thin. If the void hypothesis is validated, our cosmic address becomes a symbol of something new, a universe not defined by uniformity but by contrast. Places where galaxies swarm together in glittering webs, and places where they are scattered like dust in a vast room. Earth would belong to the latter. Our home would lie in a cosmic outskirt, a delicate emptiness that shapes the way we measure, interpret, and experience the universe. This realization wouldn't diminish our significance. It would deepen our understanding. It would remind us that the universe is not obligated to be evenly arranged or simple to decode. Instead, it may be varied, textured, and surprising. And just as explorers of old realized their home was one continent among many, humanity may discover that our cosmic neighborhood is only one type of environment among countless others. A quiet void between the louder, brighter, more densely built cosmic landscapes. Living in a void would make us observers of the universe from one of its most rare vantage points, seated in the silence between great cosmic highways. Our address would not be average, it would be a frontier. When discussing the possibility that our galaxy drifts inside a cosmic void, it becomes essential to compare this hypothetical structure to the other voids we have already identified across the universe. Known voids exist everywhere. Astronomy has catalogued them for years through galaxy maps and cosmic web reconstruction. They are not mysterious anomalies, but natural outcomes of matter clustering under gravity. Yet none of the discovered voids come close to matching the scale of the region we may inhabit if the hypothesis is true. The most famous example is the BAOs void, often nicknamed the Great Nothing. It spans an incredible 330 million light-years across, a vast bubble of almost untouched space containing only a handful of galaxies. For decades, it represented one of the most astonishing structures in the observable universe. And yet, next to the void we may belong to, even BAOs begins to look small. If our region truly stretches 1 to 2 billion light-years from edge to edge, then we are talking about something 6 times larger than the BAOs void, or more, depending where the boundaries are drawn. Such a scale borders the upper limits of what standard cosmology expects. The cosmic web is like foam, peaks of dense galaxy filaments surrounding cavities of emptiness. But these cavities are usually measured in the hundreds of millions of light-years, not billions. What is being proposed is not merely a larger version of something familiar. It is a structure that dwarfs the largest previously known voids by a factor that demands the universe be more uneven on grand scales than our models comfortably allow. Even comparing this megavoid to other massive underdensities emphasizes its significance. The KBC void, for instance, named after Keenan, Barger, and Cowie, is a local underdense region suggested to span roughly 1 billion light-years. It was already considered exceptional, though not universally accepted, and even that void is only about half the scale of what recent BAO research implies. If we live in something twice as large, the implications multiply dramatically. The void would not be a subtle dip in matter density, but a sweeping ocean of low-density space, carving out an enormous hollow in the cosmic web. Interestingly, most known voids are easily identifiable by their boundaries. Walls of galaxies that form sharp transitions from emptiness to structure. If our region is as large as suggested, however, its boundaries may be too far away for older surveys to detect clearly. We might not even have mapped to its edges yet, consider that light from galaxies billions of light years away takes billions of years to reach us. If the void extends that far, our perspective from within is like standing in a fog of emptiness too large to see across. We may only be beginning to glimpse the distant walls where galaxies gather like thick veins of starlight beyond a great hollow. This perspective reframes the significance of voids altogether. Boötes, though enormous, is an isolated anomaly, a bubble floating in the cosmic web. But if our void is twice as large or more, it may not be simply a bubble. It may be a basin stitched directly into the structure of our cosmic surroundings. Such a void could influence galaxy velocities over far greater scales than Boötes ever could. It could shape expansion rates. It could bend observational data without leaving obvious local distortions. We may be too deep inside it to recognize the shape from within, the way a person in a valley cannot easily map the surrounding mountains without climbing above tree level. Comparing voids also highlights how unusual ours would be if confirmed. Most voids host fewer galaxies, but none so thoroughly emptied across such a vast span. Boötes holds about 60 galaxies, an astonishingly low count. But imagine scaling that up. If a 2 billion light-year void maintained similar proportions, it could hold thousands fewer galaxies than expected, leaving entire regions of the sky comparatively sparse. This scarcity aligns eerily with what some surveys suggest, that our cosmic neighborhood contains fewer galaxies than statistically predicted. Not empty, but lean. Not barren, but less born. The comparison also deepens our understanding of how such a void might have formed. Smaller voids form naturally from primordial fluctuations, the same ripples left over from the Big Bang that BAOs help us measure. A void of Boötes' scale fits comfortably within this framework. Massive, yes, but expected. A 2 billion light-year void, however, stretches the boundaries of conventional formation models. Did inflation produce a fluctuation so large that it carved out a supervoid almost from the beginning? Did gravitational evolution magnify a slight underdensity into a cosmic gulf over billions of years? Or could multiple smaller voids have merged into one sprawling expanse of low density, a cosmic erosion of matter over time? These questions demonstrate why comparing voids is more than an exercise in scale. It's a doorway to understanding cosmic history. If our void exists, then perhaps the universe is not as smooth beyond certain scales as once thought. Perhaps there are more megavoids out there waiting to be discovered. Giants hidden within the haze, masked by distance and observational limits. We may currently perceive only the closest interior of a much larger empty architecture, the full skeleton of which remains beyond our reach. So when we set our possible home void against structures like Boötes, the contrast is staggering. Boötes was once considered one of the most surprising features of the cosmos. But if this new void is real, Boötes becomes almost small talk, a crater next to a canyon. Our cosmic address may be situated inside the most extraordinary underdense region ever proposed, an emptiness so large it challenges the very framework used to define cosmic emptiness. We are not finished learning what it means. The model is young, the evidence still forming, but one truth is already clear. If this void exists, it is not merely another feature of the universe. It is a statement, a challenge, a reminder that the cosmos does not owe us symmetry or simplicity. Within a vast cosmic void, the universe evolves at a slower, quieter pace. And nowhere is this more evident than in the way galaxies form. Galaxies are born from density, from gas clouds that collapse under their own gravity, from dark matter halos thick enough to gather hydrogen ignite star formation, and grow into luminous structures. In a region rich with matter, gravity draws material inward like a cosmic whirlpool, accelerating growth and birth. But in a void, this gravitational cooperation is weakened. Raw material is scarce. Gas does not clump easily. Density fluctuations remain gentle ripples instead of deep wells. As a result, galaxy formation becomes suppressed, diluted, stretched thin across unimaginable distances. This is not speculation. We see it whenever we observe known voids. Galaxies inside them are fewer, smaller, and less developed than those living in denser cosmic neighborhoods. They often lack the bright, massive spirals found in clusters. Their star-forming rates are typically lower. Their structures appear simpler, with fewer companion galaxies orbiting them. If the Milky Way lies inside a void, then our cosmic environment may have shaped our local universe in subtle but profound ways. The Milky Way might be an outlier, large and active despite its quiet surroundings. Or it might sit on the upper edge of what void galactic evolution allows. Either way, our environment influences what has formed around us, and what never had the chance to. Low-density space slows everything. Star nurseries take longer to compress. Cold hydrogen is harder to accumulate. Dark matter halos stretch, but do not deepen as quickly, meaning the gravitational skeleton needed for galaxy growth remains thin and fragile. In large voids, we'd rarely find rich galaxy clusters, those dazzling cityscapes of hundreds or thousands of galaxies interacting, colliding, and igniting waves of new star formation. Instead, we find quiet cosmic towns, fewer galaxies, greater separation, long distances between neighbors, like islands scattered across a vast ocean with no mainland in sight. If our universe were a map, void dwellers would reside in the sparsest, most remote territory, not empty, but underbuilt. If our region truly spans billions of light years, then the galaxies we see around us, including our own, may reflect the ecological reality of a sparse environment. The local group contains only a few dozen significant galaxies, and only two of them, the Milky Way and Andromeda, qualify as giants. Many others are small, faint dwarfs with slow star formation rates. This pattern mirrors what we expect inside a void. Fewer grand spirals, more dwarfs clinging to survival like shrubs growing between stones. If we lived in a dense region, our skies might show clearer evidence of cosmic clustering, more conglomerations of galaxies, more neighbors, more gravitational interplay. Another subtle consequence arises from distance. Galaxies in a void are farther apart. Interactions between galaxies fuel starbursts, black hole growth, and gas recycling. In dense regions, collisions happen often, stirring dramatic cosmic events that build stars rapidly. In voids, galaxies rarely meet. Their loneliness hinders their evolution. Without collisions to trigger star formation, many remain dim or stagnant. A void is like a cosmic wilderness, a place where life, in the form of stars and galaxies, persists but grows cautiously, slowly, quietly. This condition affects not only the present, but the entire history of cosmic structure formation in our region. The Milky Way may therefore hold a special kind of significance. Perhaps it is one of the more developed galaxies inside our underdense environment, having gathered enough mass early in cosmic history to grow big despite the scarcity. Or perhaps our region wasn't always so empty. Maybe the Milky Way formed when conditions were denser, and only later did matter drift outward, leaving us in a hollow carved over billions of years. If true, we are a survivor of an environment that gradually thinned around us. a lone lighthouse in a sea where other galaxies slowly sailed toward denser shores. Evidence supports this narrative. Surveys of void galaxies reveal that many contain older stars than predicted, implying that they formed early, developed slowly, then spent eons drifting through quiet space with limited new fuel for growth. Star formation becomes a dwindling flame, not extinguished, but sustained by smaller gas reserves. If our cosmic void hypothesis is correct, then even our future could be shaped by this environment. In billions of years, star formation in our region may fade further, galaxies may grow dimmer, and new stellar births may become rare occurrences in the night sky. Understanding galaxy formation inside voids also helps us test the void hypothesis itself. If our neighborhood is underdense, we should see not only fewer galaxies, but evidence that their evolution matches void behavior. Slower growth, less clustering, lower metallicity in some populations, different halo mass functions. Astronomers can test these predictions with deeper surveys and refined measurements, looking for the signature of quiet, slow-burn evolution than the loud and vigorous development expected in dense cosmic terrain. If our galaxies are singing the song of emptiness, we should hear it in their composition, rotation, star distribution, and halo structure. And so, the idea of a void is not only spatial, it is historical, evolutionary, even ecological. It defines not just where we are, but what we are, and why our cosmic surroundings look the way they do. If the void is real, then our place in the universe is not just physically empty, it is evolutionarily restrained. Galaxies like ours are not common products of such an environment. They are achievements of persistence in a landscape where growth is challenged, collisions are rare, and the material for creation is thinly spread. In this sense, the void hypothesis does more than explain cosmic expansion. It tells a story, a slow, dark, quiet story of galaxy life in an underfilled universe. We live in a cosmic countryside where stars are lanterns in deep night, where galaxies grow like hardy plants in poor soil, and where the Milky Way shines as one of the few great trees standing tall in a vast open field. As powerful as current evidence may seem, the future will determine whether the void hypothesis stands or collapses. And that future will be shaped by new instruments, deeper surveys, and more precise cosmological mapping than humanity has ever achieved before. We are entering an era in which we can scan the universe not as a static image, but as a layered volume of space, tracing galaxy positions, densities, and expansion across billions of light years with unprecedented clarity. If we truly inhabit a massive cosmic void, then upcoming surveys should detect unmistakable patterns, not just hints, not just statistical anomalies, but a clear picture of declining density near us and a boundary where matter thickens again, forming the rim of a gigantic cosmic basin. The most immediate tools for testing this are the next generation sky surveys already underway or soon to begin. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, the European Space Agency's Euclid mission, and NASA's Nancy Grace Roman Space Telescope will map galaxies in staggering numbers. Not hundreds of thousands, but tens of millions or more. They will measure redshifts, brightness, clustering, and motion across the sky with a precision no survey has previously approached. If we live in a void, these maps should display a gradient, a clear underdensity here, deepening toward our cosmic neighborhood, then rising outward like the slope of a massive gravity-sculpted valley. Galaxy counts and distribution should trace the shape of the void as unmistakably as contour lines trace a mountain. Even more promising, are future measurements of baryon acoustic oscillations, the relic sound waves of the early universe that have guided much of this mystery so far. Upcoming instruments will detect BAO patterns not just in galaxy distributions, but in faint hydrogen signals stretching across cosmic time. Instead of a few ripples here and there, we will gain a full 3D acoustic map of space, like seeing the universe through sonar. If our region is expanding faster due to lower density, the BAO spacing should stretch locally, then tighten farther out. A cosmological tide difference, measurable across billions of light years. The void will not be an inferred shape. It will be an acoustic silhouette stamped into space-time. Redshift surveys will also grow sharper in resolution and reach. By measuring how galaxies move relative to one another, we can detect flow, the migration of matter outward from the void toward denser walls. New computational techniques will track subtle directional biases in galaxy motion, like reading faint ocean currents in the cosmos. If matter is streaming outward from our region, as theory predicts, future instruments will detect this gravitational breeze. The motion itself becomes evidence. Galaxies inside the void should drift like embers blown from a weak fire, slowly heading outward rather than clustering inward. Neutral hydrogen mapping, especially through 21-centimeter radio surveys, may also become one of the most powerful tools we have. Hydrogen is the universe's skeleton, the raw ingredient of galaxies. If our region is truly underdense, hydrogen clouds will be distributed differently here than in denser cosmic environments. Several upcoming projects, like the Square Kilometre Array, SKA, aim to map hydrogen across cosmic time with fine precision. A giant void would imprint itself onto this data like a missing chapter, a region where hydrogen is thin, quiet, and widely spaced. We must also consider the cosmic microwave background, CMB, in future void detection. While early CMB data remains consistent with uniform cosmology, higher resolution refinements could reveal faint signatures of a local underdensity, such as lensing distortions or temperature asymmetries. If our void affects the expansion rate, it may also slightly distort CMB photons as they traverse the changing density field. Detecting such distortions requires sensitivity beyond what we currently possess. But upcoming missions like CMBS-4 may provide exactly that. Each new layer of precision acts like dusting for fingerprints across the universe. What makes this moment remarkable is that the void hypothesis is falsifiable. A giant underdensity is not a vague or mystical proposal. It must have structure, gradients, boundaries, measurable effects on light, matter, and cosmic expansion. If future surveys reveal no such pattern, if density remains flat, if BAOs show no stretching nearby, if galaxy velocities lack the expected outward drift, then the void hypothesis weakens, perhaps dissolves entirely. In that scenario, the Hubble tension must be explained another way, through dark energy variation, new physics, or unexpected early universe conditions. But if the void is real, the data will not hide it. It will stand out like the curve of a coastline finally seen from above. We are approaching a turning point. For the first time, we have the tools to map the universe at the scale necessary to prove or refute the idea that our galaxy sits inside a cosmic underdensity of staggering proportions. The next decade may bring clarity to one of the most compelling cosmological possibilities of our time. Whether we inhabit a colossal void, whether our expansion measurements arise from environment rather than new physics, and whether the universe is smooth or deeply uneven in ways we never expected. Soon, the darkness around us will no longer be just emptiness. It will either solidify into structure or dissolve into coincidence. While future sky surveys may reveal the structure of our surroundings more clearly, another powerful line of evidence already stretches across the entire cosmos. The cosmic microwave background, the oldest light in the universe. The CMB is a snapshot of the universe when it was only about 380,000 years old, and it is filled with subtle temperature variations, like faint static on a cosmic screen. These fluctuations are not random. They reflect the density of matter at the dawn of time and serve as deep clues about the large-scale structure that would later emerge as galaxies, clusters, and voids. Because of this, the CMB should, in principle, contain fingerprints of whether a void exists around us. If the region we inhabit is truly as large and underdense as suggested, then the light that travels through that emptier space could be stretched, cooled, or distorted in measurable ways. In theory, a massive void would leave noticeable imprints on the CMB through a phenomenon called the integrated Sachs-Wolf effect. As photons pass through a region of differing density, their energy can shift, leaving behind faint temperature signatures. If we live inside a void, CMB. MB photons reaching us from certain directions might gain or lose energy depending on how gravity evolved across that underdense region over cosmic time. One might expect to see cooler patches where the void slows the pull of gravity and warmer ones where matter is more concentrated. Yet the evidence is complicated. Some analyses of the CMB show hints that align with a large local void, while others suggest the temperature fluctuations could be explained without invoking such an enormous structure. Part of the difficulty lies in scale. The void proposed around us is far larger than most structures directly reflected in CMB fluctuations. The CMB captures conditions from deep cosmic time when structures were only seeds of what they would later grow into. A void stretching billions of light years may not have been large enough at recombination to leave a strong, early imprint. Instead, its influence may show up more subtly through late-time gravitational effects. How CMB B photons changed as they traveled through the evolving void billions of years later. These effects are faint, and detecting them requires data at extreme precision. Current CMB maps, including those from the Planck satellite, see only broad statistical signatures, not sharp visual outlines, which is part of why cosmologists remain cautious about drawing conclusions. There is also the question of symmetry. If we are near the center of a void, the CMB would appear mostly uniform, with distortions distributed evenly across the sky. Only if we were significantly offset from the center would the void imprint clear asymmetry, hotter spots in one direction, cooler in the other. Current CMB data shows slight asymmetries, known as large angle anomalies, but these remain controversial. Some researchers interpret them as evidence of inhomogeneity on vast scales. Others argue they could simply be statistical noise or unrelated early universe features. The void hypothesis fits the data well enough to remain plausible, yet not strongly enough to stand as proven. The CMB neither confirms nor refutes. It challenges us to measure more deeply. Upcoming CMB experiments may shift this balance. Next-generation observatories, from ground-based telescopes like CMBS-4 to potential space missions with higher sensitivity, will map CMB temperature and polarization at unprecedented resolution. Tiny anisotropies could reveal whether photons crossing our region experienced unusual gravitational shifts over billions of years. Even small distortions could strengthen the void. hypothesis dramatically, offering gravitational evidence layered atop galaxy counts and BAO signals. On the other hand, if future CMB data shows no anomalies consistent with a giant underdensity, the hypothesis would face a significant blow. A void this large should leave some trace. If no trace exists, then we must look elsewhere for solutions to the Hubble tension. The role of the CMB reminds us that cosmology is like reading two histories at once: the universe as it was and the universe as it is. One shows early uniformity, the other hints at present complexity. If the void is real, it bridges these worlds, a seed that grew into an enormous hollow over billions of years, invisible in early snapshots, but unmistakable in modern structure. Light from the CMB has crossed that history to reach us, carrying with it whispers of density, expansion, and gravitational evolution. Whether those whispers sing the shape of a void remains one of the most exciting questions in cosmology today. If the void hypothesis is compelling, it is equally riddled with deep uncertainties, contradictions waiting for resolution, questions still unanswered, and theoretical edges that do not yet align with the broader structure of cosmology. Any idea powerful enough to challenge foundational assumptions must also survive scrutiny from every angle, and the possibility of a multi-billion light-year void surrounding us is no exception. While it elegantly addresses the Hubble tension and aligns with galaxy density measurements, it also introduces new puzzles. How could such a large void have formed? Why here? Why now? And does its existence fit within the well-tested framework of inflation and the standard cosmological model? These questions form the core of the unsolved challenges ahead. The first major contradiction is scale. Voids are common in the universe. Cosmic web simulations produce thousands of them, but they almost never reach the size required by this hypothesis. A structure stretching 1 to 2 billion light-years wide pushes the upper statistical boundary of what the universe is expected to generate naturally. Standard inflation theory predicts that fluctuations in early density should have smoothed out to near uniformity across large distances. To form a void this immense, the primordial density under fluctuation would need to have been unusually strong or persistent. Did inflation fail to equalize this portion of the cosmos? Did quantum fluctuations in the early universe magnify into a massive emptiness? If so, why did this happen only here, in our observable vicinity? Another conflict concerns probability. If voids of this scale are extremely rare, then the likelihood that humanity happens to live inside one becomes correspondingly small. It does not make it impossible. Rare things happen. But it does strain the principle of cosmic mediocrity, the assumption that our position is not special. The void hypothesis suggests we may occupy a cosmological outlier, and some scientists consider this uncomfortable. They argue that explanations requiring coincidence should be approached cautiously. Others counter that rarity. Alone is not disqualifying. Someone has to live in the unusual spot, and we observe only one universe from one vantage point. Statistical arguments lose power when there is only one sample to examine. Furthermore, observations do not yet conclusively prove the void model. Evidence from galaxy surveys suggests underdensity, but not all studies agree on its depth or extent. Some analyses find the deficit modest rather than massive, large enough to influence expansion slightly, but too small to explain the full Hubble tension. Others detect patterns but cannot distinguish whether they represent a true void or a combination of smaller structures overlapping in our line of sight. The difference between a 500 million light-year void and a 2 billion light-year void is enormous. One might be astrophysically interesting, the other cosmologically transformational. Current data has not yet settled on which we inhabit, or whether the emptiness is coherent, symmetrical, and void-like at all. There is also tension between the void hypothesis and observations of the cosmic microwave background. If a void of this size exists, it should leave faint but detectable distortions in CMB photons as they traverse the underdense region. Some studies find mild anomalies that could correspond to such an effect, while others argue they fall within statistical noise. The CMB remains a double-edged sword. It neither confirms nor kills the hypothesis, but it stands as a future gatekeeper. If next-generation CMB instruments measure no gravitational imprint consistent with a void, the model weakens substantially. If such patterns appear, it may shift from fringe idea to serious contender. Another unresolved problem lies in the timeline of void development. Even if a primordial underdensity existed after the Big Bang, can matter flow alone excavate a void this large in only 13.8 billion years? Simulations suggest that voids deepen and expand naturally as matter migrates outward. Yet the proposed scale of ours requires either remarkable efficiency or an early start. Did dark matter distribution favor this region unusually? Was our cosmic location once more populated, only to thin out over billions of years? Or did multiple smaller voids merge together like raindrops converging into a lake? Each scenario is plausible, none proven. And this leads to a deeper philosophical tension. If the void hypothesis is true, then our view of the universe is biased by emptiness, meaning we may need to reinterpret decades of observations, not as universal truths, but as environment-filtered measurements. That alone is not a contradiction, but it is a challenge, one that demands rewriting textbook assumptions about distance, expansion, and cosmic composition. Some researchers argue that science progresses cleanly through such shifts. Others caution that the void model risks overcorrecting, attributing every anomaly to structure rather than considering unknown physics or new components of cosmology. Finally, there remains the greatest unsolved question of all. What if the void is only part of the story? The Hubble tension may arise from multiple causes. Early universe physics we have not discovered, variations in dark energy, unknown neutrino behavior, or structural effects like voids working in concert. The universe may not offer a single elegant answer, but a mosaic of influences, each adding noise to the cosmic beat. The void hypothesis may resolve some of that mystery, but not all. Or it may resolve everything, if future evidence draws the outline clearly enough for all to see. We stand, then, at a crossroads. Evidence hinting toward emptiness, theory resisting the scale required, observations not yet decisive. The void hypothesis is powerful precisely because it sits in this tension, supported yet unproven, elegant yet demanding, possible yet not guaranteed. It forces us to ask questions cosmology has long avoided, about our location, about uniformity, about how the universe grew from chaos to structure. Whether the void survives scrutiny or dissolves under observation, it pushes science forward. In this way, the contradictions and the uncertainties are not weaknesses. They are fuel. They drive astronomers to look deeper, measure sharper, and question more boldly. The void may remain a mystery, but mysteries have always been the engine of discovery. The possibility that we are living inside a colossal cosmic void is more than just a hypothesis. It is an intellectual spark. It forces cosmologists, physicists, and astronomers to question old assumptions, build new tools, and re-examine everything we believe we know about the universe. Science advances when the universe surprises us, and the void hypothesis does exactly that. It proposes that the cosmos may be structured in a way we never expected, that expansion may not be uniform everywhere, and that our cosmic environment could profoundly shape the measurements we use as the foundation of cosmology. Few ideas have the power to rewrite so many layers of scientific understanding at once, and fewer still do so with elegance rather than chaos. The excitement comes from its potential to solve problems, but also from the questions it dares us to ask. One reason the hypothesis is so thrilling is that it challenges the cosmological principle, the notion that the universe is homogeneous and isotropic on large scales. This principle has guided theory for decades, forming the backbone of the lambda-CDM model. To question it is to shake the pillars of cosmology itself, yet the void hypothesis does so not out of rebellion, but necessity. If local and global expansion rates disagree, if galaxy surveys show underdensity, if BAO patterns stretch close to us, then the universe may be asking us to consider that sameness is not the default we assumed. Instead, structure may persist even at extraordinary scales. The void hypothesis invites us to imagine a more complex cosmic architecture, not a flat uniform field, but a tapestry woven with contrasts. Voids, clusters, filaments, and superstructures may shape the expansion of space in diverse ways that depend on where in the web one resides. The excitement also lies in testability. Many cosmological mysteries, dark matter, dark energy, quantum gravity, remain frustratingly intangible. We cannot isolate them in a lab. We cannot probe them directly. But a void is different. It is observational, surveyable, mappable. We can count galaxies, measure redshifts, track BAO ripples with increasing precision, and analyze CMB distortions with rising fidelity. Within the next decade, instruments will either draw the boundaries of a massive, underdense region around us, or reveal a smoother distribution than current hints suggest. The hypothesis is not speculation without anchor. It is a test waiting for data. And in science, few things are more energizing than a theory poised on the edge of provability. More than solving existing anomalies, the void hypothesis pushes researchers to innovate. It demands better sky maps, finer BAO measurements, deeper hydrogen tracing, and more advanced gravitational simulations. It encourages cross-examination between fields, cosmology, stellar physics, structure formation, CMB analysis, relativistic modeling, and observational astronomy all converge around the same question. New tools must be built, new surveys launched, new methods devised to translate the faint signals written across billions of light years. Scientific revolutions often begin this way, not with answers, but with the machinery needed to find them. The idea also broadens our imagination about what the universe might be. If enormous voids exist, then cosmic structure may be more dramatic than we once believed. Deeper emptiness, brighter clusters, regions shaped like deserts and cities on a cosmic scale. It invites us to consider that habitable regions of the universe may not all look the same, that civilizations elsewhere might grow beneath crowded star fields in regions rich with matter, while we evolved under a quieter sky. This transforms astronomy from a single universal narrative into a diverse landscape of possibilities. Different environments, different histories, different cosmic contexts. It makes the universe feel larger, not in size, but in character. Even if the void hypothesis is eventually proven wrong, the pursuit itself enriches science. It forces cosmologists to refine distance measurements, calibrate standard candles, evaluate systematic errors, and re-examine observational assumptions. It tightens methodology, sharpens models, encourages caution and creativity in equal measure. This is how science grows. By stepping toward what might be true, knowing that even in failure we gain clarity. The void may stand or fall, but the tools built to investigate it will remain valuable for generations. Perhaps the most exciting aspect of the hypothesis is what it reveals about our cosmic humility. For centuries, every breakthrough in astronomy has reminded us that we are not central, not physically, not structurally, not cosmically. But instead of diminishing us, discoveries like this elevate our sense of wonder. If we are indeed floating inside a giant emptiness, then we occupy a rare window through which the universe can be studied differently than from any dense cluster or galactic hub. We are observers from the quiet zone, a vantage point that might allow us to perceive expansion more clearly, BAOs more cleanly, and large-scale structure more transparently. Emptiness, instead of limiting us, becomes a laboratory. The void hypothesis is exciting because it carries all the hallmarks of a transformative idea. It tackles a real unresolved tension. It makes predictions that technology is finally capable of testing. It harmonizes disparate observations under a single narrative. And it reminds us that the universe is not obligated to reflect our expectations. It may be more uneven, more dynamic, and more surprising than we have dared to believe. A billion light-year void does not simply change where we think we live. It changes how we ask questions. It changes which questions we believe are worth asking. It changes where we point our telescopes, how we interpret redshift, how we weigh matter against expansion. It shifts the cosmic stage beneath our feet and shows us that science remains young, even as the universe grows old. If confirmed, this would be not just a discovery, but a new chapter in cosmological understanding. If disproven, it would still have carried us forward. In both outcomes, the universe wins, because we dared to wonder whether we live in a hollow of unimaginable scale. Throughout this exploration, we've followed a thread of evidence and possibility, from ancient sound waves of the Big Bang to modern galaxy surveys, from local expansion rates to the deep glow of the cosmic microwave background, all pointing toward a provocative question. Do we live in a vast cosmic void? The idea is bold, unsettling, and electrifying. It challenges the assumption that the universe is smooth on the largest scales. It suggests that our cosmic address may be defined not by presence, but by absence. A region of space with fewer galaxies, fewer gravitational anchors, and a faster rate of expansion than the cosmos beyond. Step by step, we've explored what such a void would imply, how matter behaves inside it, how galaxies evolve under its influence, and why this environment could distort the measurements used to estimate the universe's expansion. The pieces do not confirm the hypothesis, but they fit with a surprising coherence that is impossible to ignore. The Hubble tension, the mismatch between the expansion rate measured nearby and the slower rate implied by the early universe, remains one of cosmology's most persistent and pressing puzzles. For years, scientists debated whether this discrepancy could be explained by new physics, changes in dark energy, or unknown early universe conditions. Yet the void hypothesis offers another path, that the difference may not come from fundamental forces or exotic particles, but simply from where we are standing. If we live in a region of lower than average density, then space around us would stretch more rapidly. Local measurements would read high, distant measurements low, and the tension between them would dissolve not through theoretical overhaul, but through geographic context on a cosmic scale. A void could unify the discord, offering simplicity where confusion once reigned. But the implications extend far beyond the Hubble tension alone. If a void surrounds us, stretching not millions but billions of light years, then the formation and evolution of galaxies would be shaped by scarcity. Matter would drift outward, deepening the emptiness. Star formation would slow. Clusters would be rare. The Milky Way itself might represent a fortunate survivor in a quiet region, a bright spiral in a sea of thinner gas and lean material. We would not live in the cosmic average. We would live at the edge of possibility, within one of the universe's most rarefied chambers. Our vantage point would be unique, not because Earth is special, but because the space around it lacks the richness seen elsewhere. We also considered comparisons with other known voids. The BAOs void, once regarded as one of the largest regions of emptiness ever discovered, may be dwarfed by the scale of our own cosmic terrain if the hypothesis is correct. This would not be just another void. It would be the void. A giant among giants, a hollow in the cosmic web so large that it forces us to reconsider how structure forms. Could inflation produce such a fluctuation? Could gravitational migration alone carve a hollow so vast? Or did multiple smaller voids merge into one silent gulf around us? These questions remain open, waiting for the next generation of telescopes to help answer them. We turned to the cosmic microwave background, the oldest observable light in existence, to test this idea. If a void surrounds us, photons passing through it may lose or gain energy, leaving faint imprints in the CMB's temperature variations. Some data hints in this direction, some does not. The CMB neither confirms nor refutes the hypothesis, but stands as one of the most critical frontiers for future inquiry. With upcoming high-resolution mapping, we may soon be able to detect even the faintest gravitational imprint of a void if it exists. Then we looked deep into the uncertainties, the contradictions that pull against belief. Why would we live in such a region if it is statistically rare? Can a void of this magnitude form naturally within the timeline of cosmic evolution? Why does only some observational data align clearly with the model, while other data resists interpretation? These unresolved tensions are not flaws. They are fuel. They push cosmologists toward sharper instruments, better simulations, and bolder questions. The void hypothesis may thrive on mystery, but it survives by inspiring evidence. And that is why the idea is so scientifically exciting. It is not merely a theory. It is an invitation. It pushes the boundaries of astrophysics, encourages new measurement strategies, inspires fresh cosmological tools, and forces us to confront whether the universe is more uneven than we believed. It asks us to let go of the notion that our position is unremarkable. Not because we are central or chosen, but because the cosmos may not be uniform enough for such neutrality to exist. To live in a void is not to hold cosmic importance. It is to stand in a rare silence between roaring structures, a witness to emptiness that shapes perception. In the end, the hypothesis stands like a door in front of us, half open, half shadowed. If future surveys reveal rising density beyond our region, if BAO maps curve outward like the rim of a bowl, if CMB distortions whisper the outline of a hollow in space-time, then the story of the universe will change, not collapse, expand. We will see cosmology with deeper nuance, recognizing structure not as background texture, but as a factor that influences measurement itself. We will understand that our cosmic address matters, that location shapes knowledge, that emptiness has gravitational meaning. And if the void is proven false, then the search continues for new physics, for revised models of dark energy, for deeper truths still hidden in the cosmic web. Either way, the universe remains larger than our certainty, more mysterious than our equations, more beautiful than our models can yet contain. So we close with this. We may be living in a hollow 2 billion light years wide, or we may be standing at the edge of a deeper understanding still forming. In both outcomes, we are explorers, and the universe has only just begun to speak. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.